Hey, it's Mr. K doing a video for AP Physics 1 and C. Started this video but had to restart because I forgot a crucial step. But let me just go through the intro again. We're doing the universal law of gravitation, which means, hey, if you have mass and anything else that has mass, they'll be attracted to you and you to it. And the relationship is, over here, there's a universal constant, 6.67 times 10 to the negative 11th. This is just one of the properties of our universe if you have mass. That makes the equation work out. So m1, m2, those are the two masses involved. And then r is going to be the distance between them. It's going to be r squared. And so here, we're going to start off with a simple problem. We have a person on Earth. And I had already started the problem, but I forgot one crucial thing. And that's the square on the bottom. Forgot that the last time I started this video, so I'm going to put it right there. Turns out that this person will be pulled towards the Earth, and the Earth will be pulled towards the person due to Newton's third law. No matter where you place the person, doesn't really matter where. Let's see if I can't do this appropriately. So we have the universal gravitational constant, 6.67 times 10 to the negative 11th right there. We've got the mass of the person, 50 kilograms right here. We've got the huge mass of the Earth, which is 5.972 times 10 to the 24th kilograms right there. Top of the equation's covered. And we're going to divide by the distance the person is from the center of the Earth squared. So about 6 million meters squared. And the way that this law works is no matter how big the object is, if we're on the outside of it, you can pretty much call all the mass here, you can just crumple it all down, smush it on down to one singular point in the middle. And so the distance that we are from that point is the radius that we'll use. So just to kind of double check, we got 6.67 times 10 to the negative 11th times 50 times 5.972 times 10 to the 24th. Divide that by 6.371 times 10 to the 6th power. All that bottom stuff squared. And we get about 491 newtons. And that's interesting because really, if we're doing an F equals ma thing, and F is equal to 491 newtons, then we can say, well, F is equal to ma. Shouldn't this be ma? A is going to be 50, or m is going to be 50. So 491 divided by 50. So divide this by 50, and we get around 9.8136. Okay, so that's basically the acceleration due to gravity if that's the only force on you. So hooray! So in physics, if you want to figure out the force of your weight or the force of gravity, usually we just do mg because this is a pain in the butt. So we just say, hey, g is around 9.81 and meters per second squared, and we're good. So we don't need to write all this other stuff. But here we kind of do because we're going to change the problem up a little bit. So let's say that you are not on the Earth, but let's say you are farther away from the Earth. If this is Earth's radius, r, then let's put you another Earth's radius away from it. So that's another r. So we'll have you floating out here. And the forces on you, well, if we were to look at the force on you, you would still fall towards the Earth. And so you would have a force on you towards the Earth. And the Earth would still have a force on it towards you. Okay? So if you were to just be out here, you would definitely fall back down to the planet. But the way that we achieve orbit is we give yourself some sideways velocity, so while you fall towards the planet, you actually fall around the planet, and you just miss it. So let's just kind of look at this again. What if we were twice the radius away from the center, instead of just our normal one radius from the center? And that's just going to be all the same stuff here, except we're gonna double that bottom portion. So tell you what, let's just say we have g. We've got m1, which is still us. So I'll just say us. We're going to say m of the Earth, and we're going to divide that by not once the radius, but twice the radius. And that's going to be a squared value. Okay? And so the force that we would experience, if you look at all the math here, all these numbers are the same except for that 2. That 2 is it's on the bottom, it's inside of a square, and when you really do it, you're going to have g, m us, m Earth, divided by not 2, but actually 4r squared. And if everything is the same, g is the same, this number, m's the same, e's the same, or mass of Earth is the same, the only thing different is that 4 there instead of the none that was there before. And so all we would do to figure out the new force is we'll just say, hey, it's 1/4 of the force that it was before. And so 491 divided by 4, that's about 122.75. So 122.75 newtons would be your new force of gravity at this distance out here. And if you wanted to say, oh, well, that's 122.75, that's still equal to ma, right? It sure is. Well, we're 50. So what's the acceleration due to gravity out there, twice the radius from the planet? Well, just divide this number by 50, and we get about 2.455. So you still get a force of gravity out here, but it's actually a lot weaker, 2.455 for the acceleration instead of your usual 9.8 or 10. And we're just looking at, like, how does distance away from the planet change that force of gravity? Well, apparently by doubling your distance, it's gonna fourth the gravitational force on you, and so it'll take a fourth of that acceleration due to gravity that you would normally feel. So it's not that there is no gravity out here. There definitely is, but it gets weaker to the inverse square, and that's the inverse square law. So again, force gravity does get weaker as you get farther away from the planet. Now, question would be, an AP question would be, what if you had a planet that was like Earth, but maybe it was like double the let's see, we'll just say the density of the planet Earth is the same as the density of the planet X. I don't know what it is, but planet X is going to be, let's make it bigger. So while the Earth has a certain radius, planet X is going to be like 4 times the radius of the Earth. And the question is, what would the gravitational force be like on the surface of the planet, or what would the acceleration be like on the surface of that planet? And so all we're going to do is we're going to look at this gravitational formula again. And so the gravitational formula is G m1 m2, or let's say m2, divided by r squared. Okay? And at first glance, we would think, all right, well, that's the original formula. If we go 4 times the radius, well, if G m1 m2, one of these is the planet, one of them is us, we would divide it by 4 times that radius squared, radius of Earth. Well, then this would be like 1/16 G m1 m2 over r squared. Now, hold on, because yes, the radius is bigger, but if you keep the density of the planet the same, you're going to get more mass as well. And so we kind of need to look at that too. So before we actually say, yeah, that's the answer, that's not the answer, by the way. We're gonna look at the density of the planet and how that changes. So, or how the mass would change based on the radius. So if density is going to be, what is density? Mass divided by volume. It's how much mass you have per volumetric space. We know that volume is the volume of a sphere. So what is the volume of a sphere? 4/3 pi r cubed. And so here, if we were to look at this, if we were to multiply the radius by 4 times, in order to keep the same ratio stuff, let's see, we have 4/3 pi. If I put a 4 inside of that r, that's going to be 4 times 4 times 4. What is 4 times 4 times 4? 4 times 4 is 16. 16 times 4 again is going to be 64. Yeah. So that's going to be 64 r cubed. And the mass here would have to be 64 times if the radius was quadrupled. That's interesting. So if we go back, this mass, while the radius would change, yes, the mass would change as well. And so really, that doesn't work out at all. We need to put a 64 next to this mass up here. Let me write it a little bit better down at the bottom. So G is the same as it was before. Mass 1, let's just call that us. But the planet X, would have 64 times the mass of Earth, instead of just 4 times, because the radius was quadrupled. and mass of Earth. And the radius here is going to be 4 times the radius of Earth, and that's going to be a 16 on the bottom. Radius of Earth squared. So, as we just did with the calculator, 64 divided by 16 is going to be 4, correct? Boop, boop, boop. And so, turns out that 64 divided by 16, that's 4. G, M us, M Earth is still there. This is all in terms of Earth. Radius Earth squared. So if you were to go to planet X and it's 4 times the radius of Earth but the same density as Earth, you're going to have 4 times the amount of gravity there on the surface. So G for planet X is going to be 4 times G for planet Earth. And so it's about 40 meters per second squared there. You probably won't have a very fun time standing because you're going to be 4 times your weight in the surface of this planet. So hopefully you kind of caught all that. It's just you can't make the simple assumption that because the distance is bigger then the force of gravity goes down. It does, but in the case of this planet, as you make it bigger, you got more mass there. And that's where we look at this whole density argument. So I'm going to stop the video here. Force of gravity at its basic is just, hey, what's the force between 2 masses? And it's based on the distance squared between them. There are other manipulations that you can do whenever we start to get into higher up physics or more complicated physics, I guess. But we'll keep it pretty simple for this class. All right, we'll end it here.